So now the Qiskit playground is running. Let's go and see if we can access it. So I want to point out certain things. Yeah, let's scroll down a little. There's something I want to show what happened to the secret.
Okay, should I continue scrolling?
Yeah, so you see now it has a Qiskit secret, which is mounted as a volume inside the pod at the location temp secret Qiskit secret. So this is where your secret is residing as a file. Now let's go and access the Jupyter notebook. So on the left-hand side, scroll down.
On the left-hand side?
Yeah,
yes.
Do you see networking?
I do.
Okay, so click on routes. And routes is just like a OpenShift way of exposing a URL that can be accessible outside the cluster. So in Kubernetes, you can do port forwarding, but OpenShift kinds of automates that. So there's a resource that OpenShift has, which is routes. So this is just kind of like a port forwarding. So let's click on that HTTP Qiskit playground.
Perfect. It's loading.
Okay, so now you see that the Jupyter server is running, and we have already 3 Jupyter notebooks. So I just had them by default. For people who are new at Qiskit, they can explore these notebooks and they can try the Grover search and simple Qiskit circuits. But let's now this is all yours. This is now your playground, Luciano. So
I see. So already, now I'm already running in the cluster, right?
Yeah, you're running in the cluster.
Okay, so let's open a new notebook, and let's see what we find there. So, yeah, usually my first command in Qiskit is checking for the version, the Qiskit version that I'm executing from Qiskit import. Let's see. Okay, so this is the Qiskit version that is coming already with the operator.
Yeah, and as you can see, this is old. We are releasing a second version of the operator, 0.2, and that will have the newer version of Qiskit.
Can I do this kind of things? Can I just directly run a command into the cluster like that and update it myself? Am I going to break something if I do this?
And even if you break something, we are going to fix it. That's this masterclass is about. So let's see what happens.
So I mean, we can always just like remove the playground and create a new one. That's what you're saying.
Right. Yeah. So I would say not the playground, but the libraries that the playground has. You can always update them. So.
Okay. So there is some errors though. Some permission denied. Let me see if managed install, because I see there is some things with RedWorX. Let me see if I can clear out and restart the kernel and see if this updated. No, it did not update, no.
So I think you cannot install and update the new version of Qiskit because you don't have the permission, and you are a user. Like when we create a CR, we assign a user for updation, and then we assign a user for just the using thing. So we don't have the permission to change the Qiskit, but you can install any other libraries if you want. So.
But I could install locally in my I don't know how to say, in my home directory, something like this.
I guess the -u is for the same thing, isn't it not?
Oh no, -u stands for upgrade. Yeah.
Okay. So let's try this. I think so. You should, because you are not expecting a sudo. No.
Oh, cannot perform a user install.
Yeah, right. So it won't let you update a new version of Qiskit, and that is an interesting thing. Probably we should create a issue in our repository that it should let you do that.
Okay, let me see. So there are many parts in Qiskit. The part that is more in the core is called Qiskit Terra. Let's see if I could update Qiskit Terra.
No, but I think that the problem that you are going to have is installing the graph library that is important. If you go down
Oh, the RedWord X.
Exactly.
Yes. This is the library that is used for graph manipulation.
Exactly.
And yeah, it's written in R, and that probably creates some obscure situations.
In Rust, yeah.
Sorry, in R, in Rust. Yes, you're right. R is yet another language. Yeah. Okay, but this should not be. I mean, I can work with an old Qiskit. It's fine. But let's see if I can access my my backends. First, I will import what Ismael. I'm not sure if you remember. Ismael mentioned this notion of the provider. This IBM Q is the provider. Is the part that interface with the IBM Quantum devices.
Yeah.
So
you can use other providers, and you can build your providers.
Yeah. And in a regular situation, Parul, I will do something like IBM Q save account, I think. Let me see. Yeah, same account. And then here I will put my token. But in this situation, I have already the token saved in my locally, right?
Yeah.
Okay.
I assume that.
So you mentioned that it was in a file. It was in a file, a bit of an obscure file in the temporal. Where can I find that path again?
Yeah. So go back to the pods.
The pod.
And click on the Qiskit. Yeah, the pod. And you will have to scroll down, and it will. Yeah.
Oh,
it is a temp secret, Qiskit secret.
I see.
Okay. Could you explain me again, why do I need to save the secret, or like the IBM Q save account? What is the significance of that?
Yeah, this saves locally this token, so Qiskit can access the resources to, for example, run circuits.
Okay, so this is like you have to run the circuits on the actual real machines or on the simulators on the network.
Exactly. Disconnect. Yeah, exactly. Disconnect your local machine with the devices in the other side.
I could also run the circuits like locally. By local, I not mean my laptop, but I mean your cluster.
Yeah.
But I do still need a token if I want to run them in the simulator that is in the IBM cloud.
Okay. Okay. Cool.
So let's see. Let's see if this works. So I will put the content of this file into a variable, call it A. Well, maybe it was not the best secret. Let's put secret. Let's be more didactic. Secret 0, and let's partially show my token here. Let's see. Secret is not defined, but I just did it.
Yeah, you need to check it.
You have to. Yeah.
So it didn't work.
Okay. Can you just do that? ls instead of cat, can you just do ls?
Yes. Let's see. Oh, I see. This was the directory.
Yeah. And the file name is qiskitsecret.cft.
Okay. That makes sense. That makes sense.
Okay. Yeah. Again, we're missing the file name again.
Yeah. Because the folder. And now the file. The slash. Yeah.
Perfect. That looks like a token, right?
Yeah.
So now I can save this secret using my save account secret. And this square bracket 0 is because I want just one line from that file. It only has one line, but yeah. So this should work. Let's see.
No.
Okay. So let's see if everything goes well. Let's load the account. And I will try to find my backends here. So usually the account gives you a provider object, and in the provider object you have provider dot backends.
Now I have a question here, because when I was putting my hands on, I was very confused between what is a provider and what is a backend.
Yes, it is confusing indeed, because Qiskit is trying to well, it's sorry, no, it is agnostic from the backend. you could connect Qiskit to any other company, for example, Honeywell or Penny Lane or any other quantum hardware provider.
Yeah.
And that quantum hardware provider is the provider. And that provider can give you access to several computers, like the case of IBM gives you access to several quantum computers. Each of them is a backend.
Okay.
But that's a really good question indeed, yeah. So here are all the backends that I have access in the IBM Q provider. Yeah. It's a bit hard to read it. Let me. So is the font big enough, by the way?
It's good for me, but it would be better if you can make it bigger. Yeah.
Okay. So let's see. How can I? So let's get every name, and let's also get configuration and the amount of qubits that I have in each backend. And let's see if this works. Okay, so here are all the backends that I have access with how big this backend is.
Oh.
So check it out that some of them are like real backends, real backends in the meaning of real hardware. Well, not that one. That was a simulator, but this one is a real hardware. And this one is a real hardware. And some simulators, they do run in specialized hardware. And that's why they allowed you a lot of possible qubits. So that's why the maximum qubits is so big here. And also it's because it's not for any kind of circuit, but for some sort of like a special kind of circuits that can run especially well in classical hardware. That's why the number is so big there, yeah.
Okay, question. So what is the difference between a simulator that would be running inside the cluster versus a simulator that runs on the IBM Q network?
It's the same simulator because it's
So I can even get 5,000 qubits on my local system?
Yeah, you can. The big difference is the memory. To achieve to have, example, 32 state vector simulator, you need to manage more than around of the 16 or 32 gigabytes of memory. If you don't have it, obviously you cannot simulate that. No, the problem is like every time that you add a new qubit in the simulation, you need to have the double of the memory, and this is every time that you add a new qubit.
So remember the example that you put with the caffeine molecule, right? You said I could model this with 160 qubits. But the amount of memory that you will need in a classical computer for the same model will be 2 to the power of 160, and that's a huge number.
Yeah. So, okay, so definitely even on a simulator, we cannot show caffeine configuration even on a cluster. But like otherwise, I just thought of this. Do you think instead of wasting, or not what's wasting, but consuming the actual backend, could be a good practice that people simulate on the OpenShift cluster, and once they have a foolproof program or a circuit, then they actually run it on a backend?
Usually the workflow is you try a toy model locally that you can play and get used to it and specialize the circuit. And once that you have the idea of what you want to do, you run it into the real computer. Because the back and forward, the debugging, everything is complicated to do remotely. That's usually where you do it more like locally. But also consider that nowadays, we didn't reach the point where quantum computers are as powerful as classical simulation. So currently, all our simulators perform better than a real quantum computer. Hopefully that will change at some point, and that's why IBM and other big players are betting strong on this market. But currently, you do your experiments all in simulators, except that you want, for some reason, to check it out something specific that is quantum. In that case, you go to the real backend.
Yeah, makes sense.
So in this way, I'm showing all my backends in a more nice way, I could say, like more eye candy friendly way. These are all my backends that I have access to. Some of them, for example, are real Well, these ones are all real computers, but some of them are like really funny, right? Like this one, for example, is only 1 qubit, right? So you can simulate a single qubit circuit here, for example. Well, you can run actually because it's a real hardware. And you will get here in this table how big in terms of how many qubits you can run in that computer. But also the real size of a quantum computer is defined by something that we call the quantum volume. Because the quality of computer is not just enough to say, okay, I have 1,000 qubits. Also, it's important to see what is the fidelity, how noisy those qubits are. And that notion is captured by this single number, the quantum volume. So even when these two computers, they have 5 qubits each, this one is much better than this one because it has double the volume. So that means that it's better in terms of error. And we're going to jump into this notion of error in a second. Okay, I think we're ready to start writing our first quantum circuit. And we didn't explain yet what it is, the quantum circuit. So let's.
Well, there are a question someone asked about what meaning this representation of the connection of the qubits.
Yes, that's a really good observation, right? These are 5 qubits that are like in this constellation, and some of those qubits are connected, and some of those qubits are not connected, and that means that these qubits that they are not connected, they cannot interact. That has interesting consequence for the problem of compiling and transpiling a quantum circuit. It's something that hopefully, if we have the time, we're going to jump on later. But how well connected your qubits are is also a key element on the quality of your computer.
Yeah, and one of the things is not connected physically, but you can use some kind of algorithms to connect and make entanglement from one to another without have direct connection. The problem is like you need to spend or inject more code in the middle that make more or less efficient the execution of the code. But yes, it's possible to make entanglement from all of these qubits. But yeah, the better thing is to try to use the qubits that is more near. Okay, you can continue. Thank you.
We were going to create our first circuit here, quantum circuit. It's going to be we're going to use only 1 qubit, and the first thing that we're going to do is to run an operation on that qubit, the qubit 0. We're going to do the operation of that is called X, but probably most of the classical programmers are more familiar with the operation not. Basically, if you have a bit that is in 0 and you apply the operation not to that bit, you will have a 1 at the end. And the operation X does exactly that. So let's see how that works. Okay, I have some errors because I need to install another library. I hope this works. Let's see.
No, that will work.
Oh, I see, because it's a new library, as you said. Mm-hmm.
Yeah. You don't have to access to the directory which has Qiskit installed because it came pre-installed, but you can still install things inside your user directory.
I see. Gotcha.
And that was done by a sudo, so that's why the permission is not there.
Okay, let's see if this works. Mm-hmm. Okay. Oh, it did work. Perfect. Thank you, Parul. So yeah,
the hello world of Qiskit. Can we say that? Is this the hello world of Qiskit circuit development?
Actually, it's even smaller, I would say, because it's not using any quantum property. It's very classical in some sense, right? Okay. The qubit Q is in 0, and then we apply the gate X, or the operation X, and then we're going to measure what's going on after that, and hopefully we're going to read a 1. And that's exactly what classically happens, right? Everything that you can run in a classical logical network, you also can run it in a quantum circuit. That's in that sense, the expressibility of a quantum circuit over seeds. You can run everything that you already can run classically, plus some other things that we're going to jump on those extra things that you can do with quantum computers in a second. But you can be as good as a classical computer in terms of expressibility. But also, as you mentioned in the first part of the talk, makes no sense to run in a quantum computer things that you can already run in your classical computer, because your classical computer will have less noise. And let's see what that means in the next coming line. So the first thing that we're going to do is to find a backend. I will use this single qubit backend, IBM Armok. So I will say here, provider, get backend, and I will get my backend. And I will run in this backend, I will run my circuit. And I will put the result of that in a job. So, oops, let's see what's going on. Quantum circuit has not to dictionary. I have no idea what that means. Let me see what I have done wrongly. Oh yeah, no, because this is an all this
All
is all
version.
Qiskit,
Okay.
all Qiskit, and yeah, this is we do it the old way. Import, execute. We're gonna need this because we are moving away from this execute form. So now it's circuit and backend, and this is the job. Let's see if that works. So in this way, we send the circuit to execute to our real computer, to IBM Armok, and let's see what is the status of this job. So it's actively running in the computer right now. Let's see, still running. Oh, it's done. Perfect. Result. Get counts. And let's see. So by default, every circuit is executing a computer 1024 times in something that is called a shot. So you can tell your computer how many times you want the execution of that circuit, and by default is 1024. And we see here that most of the time the answer was 1, but sometimes the answer was not 1, it was 0. And this is one of the problems that we mentioned before, right? Quantum computers are noisy. Yeah. The result that we are getting is not always the right one, and that's why we had to run the same circuit several times in order to extract the right answer out of it. In this case, you know that the right answer is 1. Go ahead, Ismael.
Another clarification. No? You need to execute this amount of times, these shots, because the result is not a classical result. It's not yes or no. It's a probabilistic result. This means it's like every time that, because one of the big characteristics or the main characteristics of these or features of these quantum devices is like every time that you manipulate one qubit, okay, the qubit gets one state. And the state can be something that is 0, 1, or something in the middle. That is the thing that I'm sure that
superposition state. Is that called the superposition state?
Yes and no. It's like every time that you read a qubit, you can have 1 or 0. That the sample of the previous circuit, you can see that for these noise reasons, or noisy reasons, you can get 947 times 1, but there are some times that you get the 0, because it's a probabilistic thing. No? When you measure, when you read a qubit, the qubit collapses in 0 or 1, because can be a little bit near to the 0 or near to the 1, but this a little bit can make that when you read the answer of the qubit is 0, 1, because every time that you read, you only get the 0, 1. But if you don't read nothing, you don't measure the qubit, they are in one state that is a probabilistic from this 1 or 0, and the probabilistic is the final result.
So it makes
but it's definitely connected with the notion of superposition that we can explain immediately now. Yeah.
Yeah. Now Luciano,
specifically the noise coming out from this particular kind of example is coming from something that there are many kind of noise. And the one that is affecting here is what is called the measurement error. Basically, it's very hard to set the state of qubits in a quantum computer, and it's also very hard to measure the state of a state. And what we did was exactly that, right? We first set the state as 1, and then we try to measure that 1 out, and that operation is the one that is noisy, and therefore is the one that creates this effect. I think the effect that Ismael mentioned can be clearly seen in this following example, where it's going to use a different operation that is called H or Hadamard. And this is exactly the one that you mentioned, Parul, the one that puts that qubit into a superposition. And what that means that when I read the state of this qubit, I'm going to have 50-50 chances of that qubit being a 0 or that qubit being a 1. And let's see how that works. So let's get our count. So it needs to wait a bit in the queue. In the meanwhile, we are going to...
I have a question. So you said the default number of shots is 1024. So is it like a sweet spot that you have determined that for that it gives the best result? Like you can do it 2000 as well, but you still get like a...
Yes, that's a really good one. I mean, you may want to have more shots if, for example, you have more than one possible result.
Exactly.
But that also creates other problems, like, for example, the fact that creating like several shots, they are not equal, they don't have all the same quality. The shots that you did at the end, they are less, they are more noisy than the ones that you did in the front. So where is the probabilistic of your result popping up is something that you need to decide by mostly try and error. And that's why many simulators, they do have something that we call noise modeling, where you can, in your simulator, model noise, and in that way, you can check it out where is that sweet spot for the specific problem that you want to solve. And in that way, then when you run in the real computer, you don't have to think about those things, at least not in such a big detail.
Okay, gotcha.
So in this case, for example, half of the time was 0 and half of the time was no, because exactly the situation that Ismael was talking before. When we read that superposition, it collapses half of the time to the state 0 and half of the time to the state 1. Let's run now in a I would like also to show you something that is sometimes useful to see the results, which is with time, your results, they may get quite complicated to read in terms of this dictionary. So we have a way to show those in a graph that sometimes is much better for the sake of readability. Here you can see how far are these two results in a histogram.
Yeah, this is really cool.
Okay, let's jump on a slightly more complicated situation, which is what is usually called the Bell state. And you mentioned before, which one is the hello world of the quantum world? I would say that probably the Bell state is one of those ones, because it has two elements. One is the superposition, and the other one is the entanglement. So we're going to entangle the two qubits, and basically what that means is that we're going to make them depend one of each other. So one qubit will depend on the other one. And let's see how we can have that. So we can create another quantum circuit, but this time with two qubits. And we're going to apply the Hadamard gate on the first qubit. And we're going to apply a 2-qubit gate, call it CX, on the first and second qubit. And let's draw this for the sake of seeing how it looks like. Oh, and I forgot about the measurement. Secret measure all. So what is this CX doing? This operation is sometimes called the CNOT gate or the control NOT gate. And that, in classical terms, you can see it as some sort of like a conditional. I'm oversimplifying a lot, but basically what it does is applies the gate NOT to the second qubit if the first qubit is 1. If the first qubit is not 1, does not apply anything to the second qubit. And again, I did a kind of like a gross oversimplification of what this gate does, but I think that should be enough for seeing it running and see how this works. And let's now run into instead of in the cloud, let's run it locally because we don't have to wait until the backend finishes with our job.
That reminds me, when I was doing this development, there was also option to queue your job on backends that supports that number of qubits, right? Like, what if like the backend that it gets scheduled supports 5,000? We are not there yet, but like supports 25 qubits, but I only need 2 qubits. So we also have provision of not blocking the hardware that can support more qubits for a smaller qubit. So one of the option is use select a backend that is capable of solving that many qubits, and you let the backend with higher qubits free. So is it this is what I think, but is it true, or it's like just something I made up?
No, in this moment, that part is manual because, like we said, no, this is more focusing in researchers, no. But yeah, in the future, this is some of the element that we need to have in consideration: how optimize each circuit for different hardware, no. Like you said, no, if I only use 5 qubits in my algorithm, and I have different hardware, one of them can fit the 5 qubits the execution and all the 25, obviously the system, the platform are going to redirect to you to the 5 qubits. No, there are other conversations and other research thinking in how, example, fit in a big quantum device different small circuits. That is other option. No, it's like thinking several users that each user executes 10 qubit device and you have a 100 qubit device. It's possible that you can fit, but again, there are other complications related, like in classical computing.
That is cross-talking noise and that kind of things.
Exactly.
But it really reminds me how share time in old mainframes used to work in the 70s and 80s, right? You collect some jobs in a batch and you send them to the mainframe and you share the time among them. So the kind of problems that we're having with quantum computing at the current state of the art, they are very similar to the kind of problems that we have with classical computers like 30, 40 years ago.
Mm-hmm.
In fact, related with this problem, this kind of problem is like thinking in the connection between some kind of comments from Luciano and Parul. No, when Luciano said that every time that you add a new shot, okay, for the physical reasons that is. The quantum computer, you need to think that the quantum computer is an analogic device, okay? And something that happens every time that you interact with this device, okay? This device changes the temperature, change things that finally create more noise, and that is the reason because any kind of time we need to recalibrate to try to get again the most optimum state to finally to make the operations. No, this is from one side. No, taking that in consideration, other things that the researcher is looking for or working on is it's possible to take your 10 qubit device program and split your program. It's like replicate your program in 100 device machine, okay, and put 10 times your program and reduce the number of the shots. That is other option. No? It's like there are a lot of, again, like Luciano said, it's very similar to some kind of classical problems that we have in the past coming again, and we need to refigure out all the things again.
Yeah, with a new view on top of the old problems, indeed. Yeah. So let's see the result of the execution of our hello world, of our build state. Let's see, half of the time both qubits have been reading in 0, and half of the time both qubits have been in 1. And somebody mentioned recently to me that that quantum circuits are a bit like a lazy lambdas in classical programming. Basically, once that we read one of those qubits, we collapse the state of the full system into a deterministic situation of 0, 1, right? So, and that means that only when the qubit 1 is in state 1 means that the qubit 0 is in state 1. And they cannot happen cross situations, right? So because these two qubits are what is usually called entanglement. And going back to the situation when you mentioned before, Ismael, here in these graphs, what these graphs are telling us, these constellations, means that you can only do a qubit entanglement between certain qubits here. And let's see how we can solve that problem if we have a more complicated scenario. Another thing that I would like to mention is the fact that this H gate, this Hadamard gate, is not part of what is sometimes, but it's not part of necessarily of the instruction set of the computer. So if we take a look to the for example, to the backend that we saw before, which one it was? Ambrock, right? Let's see where I have it. Oh, here it is.
Yeah.
Okay. Okay, but it loaded before. Okay.
It's possible that you need to check it from the top.
Okay. But didn't I already? Oh no, because now I'm working in the local cluster with my local simulators, right? So let's see. So IBM Q.
So your backend variable is having the, and it is representing the local simulator.
Exactly. Ah, yeah, that's a good point that I didn't mention. Indeed, yeah. When I brought Air is the name of the Qiskit simulators. We have them in a package called Air. And yes, that was an important piece of information that I missed, indeed. So Air will give you several kind of simulators, and they are part of Qiskit. So if you install Qiskit in your laptop, that means that your own laptop will run the simulation. In our case, the simulation is running in your cluster, but basically in the locality of the classical locality of Qiskit is where this Air runs. Mm-hmm. Yeah. So let's see again. Import IBM Q, load account. And I will put this in a provider. Oops. And provider, get backend, and in particular one, call it IBM Arc, right? Was it? And this, let's save it in backend. So if we see the details of this backend, I don't know what's going on. I have no idea what's going on here. But let's see, properties. Oh, now I'm entering in a place where I didn't practice for this. So let's debug this together. Gates, maybe, I don't know. Let's see what gates means. No. I don't know why this is not working. Local variable. Okay. Yeah, we used to have gates, call it U1, and we don't have them anymore. So this is part of the running an old Qiskit. Let's see if I can access this configuration.
So the culprit is the old version of Qiskit.
Yeah. Let's see. Oh, oopsie. Sorry, I moved from the tab. And let's see if I can access the basis, what it's usually called.
Yeah, these are basis gates.
Basis gates. Perfect. Yeah. I was trying to remember what it was some months ago, which is the version that you have in your cluster. Okay, this is not a color. Okay. So the gates that this hardware can execute are ID, which is basically the identity operation, and then a set of operations called U1, U2, and U3. But none of these operation is called H. And one of the processes that Ismael mentioned very quickly in the past was like, we need to compile this circuit in order to make it run in a certain backend. And what that means is basically two things. It means that we want to make sure that the instruction set is the same one. Basically, we need to convert this U into something that can be expressed in terms of these gates, and that the CNOT gates are fit in the constellation of qubits that we have before, in this map, in this graph of qubit that we have before, right? That we can connect, for example, qubit 1 with qubit 0. So if we try, for example, if we try to run our 2 qubit circuit into ARMOC, will not work just basically because it does not fit, right? Execute. Let's make it fail. Circuit. And then backend. And this fails because we're running a 2 qubit circuit into a backend that only has 1 qubit. So let's get another backend that can run more circuits, bigger circuits, and let's make sure that it's not super full, because otherwise we're gonna wait forever. Okay, let's go with Lima. Okay, let's go back. Let's bring Lima. And let's execute it. Oh, I didn't. Oh, I missed the job. So execute will make sure that the circuit fits in that backend. And I would like to show you a bit more how that works internally. For that, I would like to show you a bit how the transpiler works. Or I think I can do it directly. Import transpile. Yes. So the transpile, it's the process that will make this transformation. Why we call it transpile and not compile? And this is a bit of a language, like formal language is the reason for this. In a compilation process, you take, for example, C code, and you convert that code into an object code. So the input on the output has different types. In a transpilation process, the type of the input and the output is the same. So you can run this process in a loop. In this case, for example, the transpilation process takes a circuit and returns a circuit. That's why we call it transpilation and not compilation, which is it's a bit of a formal reason why we changed the terminology there. Yeah, let's call it transpile our circuit, and let's transpile, and we have to give the circuit and the backend. And let's now draw this. And as you can see, the circuit does not look much as our first circuit, right? Now it looks longer, bigger, and has more gates. So let's first go with the bigger one, right? We mentioned before what happened if you put a small circuit into a big machine. And the solution that we don't have right now is basically you put those wires as idle. You just put them there and they do nothing, what is usually called ancillas, and that's what it does. Then our 2 qubits, they will be allocated in qubit 0 and qubit 1, and the operation H, it was decomposed in all this sequence of gates, which is the gates that can run by the backend. That means the instruction set was converted from H into this instruction set, CNOT is supported, so this one did not change, and then we make the measurement. And this is the real circuit that runs when we did this. And this creates, of course, even more noise, right? Our circuit now is deeper and bigger, and that creates other sorts of noises. So let's see if our job finishes. It's still in the queue. Well, it was a long queue. So let's see if at some point we can get our circuit back. What is called it again? The command for see the status of all the backends. Qiskit backend.
I am not the right person to answer that.
Okay. Even getting the status is hitting with us. I guess everybody in Think21 is trying to run circuits right now, so that creates some funny process.
So okay. Lemur has 11 pending jobs.
Yeah. So we had to wait until our place in the queue gets the. Let's see if we're still in the queue. Still in the queue. Okay.
So is this the queue for only free tier, or people who are on the network, they also have to wait for the queue?
Actually, because I'm using a free account, the account that we just created together during the talk, probably my priority is the worst one. So I kind of like in the back of the list. Probably if I have using my IBM account, I will have, I hope that IBM gives me some priority in the queue, but I'm not even fully sure of that. Also, IBM queue have members have access to priority in the queue. So if there is a lot of IBM customers that they are using that, they will jump in front of me. So that's yet another of the problems of accessing the computers with a free account. But hey, we have access to a free quantum computer, so I wouldn't complain a lot.
Yeah, me too.
Finally, it's done. Let's see if we got our result. And get counts. And I will put also this into my plot histogram thing. Okay. So now more the noise is popping up, right? Now there are two correct answers, 0, 0, and 1, 1. However, the 0, 1 and 1, 0 answers, they are like, they are bothering you because noise. How we can prevent noise? Well, there are some techniques. We can be smarter in the way that we create our circuit. We can be smarter in the way that we compile our circuit. Also, we could there are techniques for noise mitigation, but the most fundamental thing that we need to reduce the noise is to improve the hardware, and that's something that IBM Research is doing to push further the hardware, and that's one of the reasons why this quantum volume measurement is so important, right? Because it's not enough with having a computer with a lot of qubits. These qubits, they need to have good fidelity. If I have a lot of qubits, but they roll a dice every time that I measure them, I don't like those qubits, right? They are basically random. I will never distinguish which one is my right result. So I don't like those kind of qubits. I want qubits that they are not just a lot, but they also have low noise. Let's see if we can force a bit more our transpilation. So one of the things that you can do is to have this optimization level, and it works a bit like GCC. 0 means no optimization at all. 1 is the default, some optimization, and 3 is the maximum optimization. Let's see if indeed maximum optimization works. This circuit is so simple that it made no difference. But let's try to make a circuit that is more complicated, and let's see if we can see the effect of optimization level in the transpilation process. So let's see. You know what? Let's do it like and H, and I will apply H to several of them. I will apply other rotations, other operations. This one is a rotation in the X set. I don't know, something like this. My point is just to create a long circuit to see what's happening. Let's see if this works. No, I did something wrong. Oh, yeah, sorry. I think I can do this to say that I can apply H to all of them. Let's see. Yeah, it works. Circuit row, MPL. Yeah, okay. This looks nice. Okay, I can apply this one to 0, 2, or 2, 3, and 4. And let's apply some. That is a 3-qubit operations too. For example, CCX. That we can apply it to 0, 1, and 2. So CCX is like CX, but with an extra control. So both of them, they have to be 1 in order to the X gate to be applied. And also you have, for example, like if your conditional gate is not an X but another gate, for example, I'm not sure if this would work. No, it did not work. But maybe this one. Oh, yeah. This one, for example, is a control Hadamard. This gate only will apply the Hadamard gate into the Q0, into the Q2, if the Q0 is 1. Let's see what else. Let's see other operations that we have. Let's apply some CNOT gates around, just to force the transpiler to do some job. Okay. So our circuit looks like this one, and let's transpile it again as we did before, and to see what's the result of it. Okay, it's taking some time. This is always a bad sign. That means that it takes a lot of time to optimize the circuit.
And it is applying the optimization default 1.
It's applying the optimization 1, yes. Okay, well, our circuit is several lines long. Okay, our goal was to give some work to the transpiler. I think that we accomplished it. And one way, for example, to measure how good is this transpilation is by checking out the depth of the circuit. And what is the depth of the circuit? It means like the amount of the amount of operations non-simultaneously that you can do in this circuit, right? If you can apply an operation simultaneously, that counts as depth 1. But if they have to be serialized, that counts as depth 2. And the reason why the depth is so important, because one of the main source of noise is something that is called decoherence. Basically, as time passes, the property of the qubits is getting lost. So when you have more operations that you cannot apply in parallel, that means that the circuit takes longer to execute, and that means that you have more decoherence, that the qubits are not preserving these quantum states that we want. And that's why the depth is a good measurement of how hard it will be to get your execution. Let's see if this, we can improve it like this with an optimization level 3. And let's see if we see the difference. Oops, something exploded. It's not possible to Okay, the instruction set did not work. The instruction set converter, the thing that translate the instruction set exploded. I have no idea why, but yeah, that's what happened. Let's see if instruction 2 make it. It didn't. Okay, that's it. That's bad. That's a bad thing. I don't know what happened. I don't know how can I solve this. Method? No. Yeah. Translation method is a parameter we can give in order to say specifically which way do we want to use to transform the instruction set from the circuit into instruction set of the computer. I don't remember the parameters here, so let's see the documentation to see what are the possibilities there.
We also have a question in the chat.
Go ahead.
So the question says, can you clarify are quantum circuits / programs number of qubits and even quantum computer specific? As in, our quantum circuits depends on the number of qubits and even the quantum computer. And do they need to be refactored to run on different computers and providers? Are there ways of solving problems with higher level abstraction?
There are a lot of questions there. Let's start from the last one. That's probably the one that I have fresh in my mind. There are ways to have higher levels of abstraction. Yes, you can instead of writing your secret by hand, you can say, Qiskit, I want to solve an optimization problem. And for that, you will use a library called Qiskit optimization that runs on top of Qiskit core that handles the secret. And you will set the parameters of your optimization. You say, okay, these are my restrictions. I want this solution in so many iterations. And you will get out of that a circuit that you will put into Qiskit core, and then you will get the result out of there. So that there are higher levels of abstractions. That's possible. There are some caveats there, right? In the current state of the art of quantum computer, the more abstract you get, the more control you have in the circuit, and there are chances that your circuit is less optimal. So many researchers that they do domain-specific quantum applications, they still run the circuit by hand because they want to have control on exactly those things. And that's something that is easy to see, right? For example, if you're running a very abstract language in a classical computer, if you're running Python, probably the assembly that is being executed, it's very inefficient in some sense. You could write your own assembly, but of course, it's more work to do that. So you use that abstraction even under the price of having less optimal results. But because performance is so critical in the current state of the art, that's why many researchers, they still write their secrets by hand. Remind me any of the other questions, because now I got lost here.
So they're asking, can you clarify if quantum circuits are dependent on number of qubits or even quantum computer? As in, like, if you have to write the same circuit, would it change if you increase or decrease the qubits, or if you have to run on a particular kind of backend, if I'm getting it right?
Yeah, a circuit in general is very abstract from the backend. You can run a circuit in any quantum computer. Of course, if the computer is bigger, it's fine, right? You can just not use some of the qubits. If the computer is smaller, well, then there are some techniques there to break some situations of very big circuits into smaller circuits, but that may not always be possible. So there was an article in Nature 2 weeks ago that tackles exactly this problem, the problem of a very big circuit that does not fit in the computer, but in some situations explains how that big circuit can be break in small circuits that they do fit, and therefore you can run them. So basically your circuit needs to be less than, in terms of qubits, needs to be less than the amount of qubits that your hardware supports.
Okay, and I have a question. Just because you were talking about Python versus the assembly language, so when I run the circuit, I am using Qiskit libraries or the SDK, and when it goes and actually is executed on the backend, does it gets it? I am assuming it would be in the form of an assembly language or in form of Quasum code, right? Is that correct?
Yeah, what Parul refers to Quasum code is to a way to represent a quantum circuit into the following text.
Yeah.
So there is this language called Quasum. That is a way basically to write a circuit. And the reason why it was called Quasum was because it was trying to be similar to an assembler language. Indeed, actually, it's a very bad analogy because you are not running Quasum in the real computer. What you are running, it's actually a sequence of pulses. So there are also researchers that they want to have such a level of control on the circuit that they run the pulses themselves. The Qiskit provides you a way to define these pulses, and you can express your circuit in terms of pulses. So those pulses are the ones that they are being run in the computer. That's the lowest level of abstraction. Quantum assembler is just a human readable way to see a circuit. Sometimes quantum assembler is used for serializing a circuit to just put it on the wire, but that's not what's running the real computer. Yeah.
Okay. Yeah. Thank you.
Okay, I'm trying to debug this situation because our old Qiskit, but I'm failing miserably. So I don't know, what can I do?
You can show if the thing is to try to show what is the optimization. Here you can use the Quantum Lab if you need it.
Oh, that's the great idea indeed. Yes, because we can run anyway locally here. That's perfect. Yeah, thank you. Okay, it seems like I'm got log off from here.
Because it's possible that you are crossing the cookies or something like that with the other account.
Ah, that could be. Maybe if I create a new file. There it is. Okay, perfect. So let's create our circuit here. Now. Thank you, Ismael, because I really was lost in what it was. How we can solve this. Okay, let me make the font slightly bigger.
Command plus.
Okay, awesome. So let's get our circuit nice and running. Perfect. From Qiskit, import, transpile. Oh yeah, and also I need my backend, right? So let's see. I think it's better if I just run it by hand. Provider, IBM Q, load account.
You have this down in the previous cell.
Oh, awesome. Get backend. And we say the IBM Q Lima, right?
Yeah, something like that.
Oopsie, I forgot to save this.
No.
Awesome. So let's see the depth. By default, it was 1,000 something, right? Oh, we improved that much in Qiskit in these last months that we are getting a better, better result even with the optimization level 1. Let's see if we can improve it even further. So probably now, if I do 0, probably we'll get the bad result. Not even, my God. So 3, 97. It's even, yeah, it's improving a lot. So So that's why the technology on the compiler is so important, right? Because this 1,000 qubit that we had to run before, some versions of Qiskit before, now we could reduce that to 97 gates, to 97 in the depth. The reason why I'm talking so much about the transpiler is because I work in the transpiler, but there are so many other parts of Qiskit that it's an open source project, and they are moving a lot and quite fast. So this is the moment for Champ in these kind of things. There are a lot of classical problems, optimization problems, how to improve the circuits, how we can express these abstract problems into circuits. That is one of the attendees' question, and I invite you all to visit Qiskit.org to learn more about how you can contribute with Qiskit. You can be part of the community. Again, it's open source. We do also nice events, and you can really find your niche here, right?